In this lecture, we'll discuss about serial in, serial out shift register. This serial in, serial out can be right shift register or left shift register. For example, if I apply input at left side, it will become right shift. Suppose if I apply input at right side, it will become left shift. So in this diagram, I am applying my input, serial input at left side. So it will become right shift, serial in, serial out shift register. It is also called synchronizer. Okay, so this register can be with any number of bits. It can be 2-bit register, 3-bit register, 4-bit, and so on. For example, I taken 3-bit register. So how many bit register we take, that many flip-flops we need. So it is 3-bit register, so I taken 3 flip-flops. That also we have to take only D flip-flops, because in the registers we just need to shift the data, move the data, but the data input, whatever the data we given here, same data should come out. Okay, so only D flip-flop suitable, because that will give same data. Whatever the data we apply at input, that will give same output. Okay, that's why we use only D flip-flops in the shift registers. Okay, so here I connected clock, positive clock, and I connected reset also. Okay, we can use any clock, positive or negative. We can use any reset, positive or negative, no issue. Okay, so when we applying serial input, suppose if I am applying at the left side, I will apply serial input to leftmost register, and when I taking output, rightmost register will give the output. Suppose when I apply input at right side, rightmost flip-flop will take the serial input and the leftmost flip-flop will give the serial output. Okay, why it is called serial in? Because input data going bit by bit. So I taken 3-bit data. This left side one become the MSB, this right side, this 0 become the LSB. So first LSB will go, then next bit will go, then MSB will go. So bits are going one by one. That's why serial in. We are giving input one by one, bit by bit. And here first we will get the LSB first, then we will get next bit, then at last we get MSB. So here output also we are taking bit by bit. That's why serial out. So here I assumed this flip-flop as D1 and the output is Q1, and second is D2 and output is Q2, third one is D3 and the output is Q3. Suppose it no need to be D1, it can be D3, and it can be D2, it can be D1. Like that also you can assume. Or some people they start with D0, then D1, then D2. Like that also you can assume. That's why here I mentioned either it can be Q3. You can start with Q3, or you can start with Q0. Anything okay. Okay, right. Now we'll see the working. So to know the working, we have to draw the table like this. So here we have to take the clock, because why we need clock? So here we have to send 3 bits. So at first clock edge 1 bit will go, at second clock edge another bit will go, at third clock edge another bit will go. But after 3 clock pulses we won't get output. In, serial out shift register, to get the same data after shifting at the output side, we need to apply 2n-1 clock pulses. Here n equal to number of bits in the data. How many bits? 3 bits. So n equal to 3. So to shift this 3-bit data, we need 2n-1 clock pulses. It means 2n-1 means 2 into n, 2 into 3, 6. 6 minus 1, 5. So after applying 5 clock edges only, we can get the output. Okay, for 3-bit data, we need 5 clock pulses. Remember that. Okay. Suppose if the data is 4-bit, then we need 7 clock pulses, like that. So here first in the table we have to write clock, then we have to write whatever the serial in data we are applying, that we have to write, and this is the output of first flip flop, this is the output of second flip flop, this is the output of third flip flop. What is the first flip flop here? Wherever you applying data, that will become the first flip flop here. Suppose if I am applying data here, this will become first flip flop, like that. So now initially the outputs we have to assume 0. So when I don't apply any data, I have not applied any data here. In that case, what is the output of each flip flop? 0, 0, 0, like that. Assumption. We have not applied any data. Here clock pulse 0 means we have not applied any clock pulse. That is the meaning. Okay, when no clock applied. And when you not applied any clock pulse, you won't apply any data. So this dash also indicating we have not applied any data. Okay, so before applying clock and before applying data, what is the status of this register? All zeros. Output of all flip flops are zeros. Okay, now I will apply first clock pulse. When I apply first clock pulse, what will happen? This 0 will go. This 0 will go to this flip flop. Okay, LSB. So this is the LSB that came. So that will go to inside. This is the LSB that will go to inside. So it came here. Then what will happen? When this bit go inside, whatever the bit here, that will move here, and whatever the bit here, that will move here, and whatever the bit here, that will become discard. Okay, removed. So here what happening? First this bit went. So this already existed Q1 go to Q2, and already existed Q2 go to Q3, and this Q3 bit will become discard. Okay, so after one clock pulses, what is the status? Q1 is 0, Q2 is 0, and Q3 is 0. Okay, now we'll apply second clock pulse. When I apply second clock pulse, second bit will go this 0. Okay, so when it go inside, this data will shift. This 0 will come here, this 0 will come here, this 0 will become discard. Now third clock pulse. When I apply third clock pulse, this last bit, third bit MSB will go. So this is going inside. When it go inside, this will come here, this will come here, this will become discard. So here all bits completed, but still we need 2 more clock pulses to get the output completely. So for this 4 and 5 clock pulses, we have to assume the data input as 0. Okay, so 0 is going, then this 1 will come here, then this 0 will come here, this will become discard. Okay, now this 0 is going, then this 0 will come here, this 1 will come here, this 0 will become discard. So 5 clock pulses completed. Now after 5 clock pulses, if we observe the output here, because Q3 will give the output. So here we are getting serial out at the Q3. Okay, so which bit will come first? So we are giving 0, that 0 will come first. So 0 will come first. Where 0 is coming? See, at Q3 when we apply third clock pulse, that 0 coming. So this will be the LSB, and this last bit will be the MSB, because this MSB is coming at last and LSB coming at first, before the LSB, before the MSB. Okay, so now we'll draw the timing diagram for this table. Okay, so that you can understand how to draw timing diagrams also. That will help in so many places when you working with other registers or counters or sequential circuits. Okay, right. Now we'll see the easy way of drawing timing diagram. So in our design, how many clock pulses we needed? 5 clock pulses, and we are using positive edge. So draw 5 positive edge clock pulses. Okay, so I drawn like this. This is 1, 2, 3, 4, 5. Okay, so before I applying first clock pulse, what is the status of this Q1, Q2, Q3? We have to list here. This is the clock pulse, and here we have to list Q1, Q2, Q3 outputs. Okay, right. You can start with Q3 or Q2, Q1, anyway, no problem. Okay. So here before applying first clock pulse, what is the output? of each flip flop. See here, before first clock pulse, it means when we not applied any clock pulse, what is the output? Q1 0, Q2 0, Q3 0, all are zeros. That's why all are zeros. Before first clock pulse, all are zeros. All are zeros. You have to write like this. 0 means low. Then at first clock pulse, what happened? Yet to first clock pulse, what are the outputs? Again all are zeros. At second clock pulse also all are zeros. 3 all are zeros. So continue this 0 for first clock edge and second clock edge also. Okay, 0 0 0 0 0 0. Now at third clock pulse, what is the status? Q1 is 1, remaining 2 are zeros. Q1 is 1. So this Q1 at third clock pulse, it has to go to 1 because Q1 is 1. And this is still Q2 0, Q3 0. Continuing. Okay. At fourth clock pulse, this Q1 is again became 0 and Q2 became 1. So at fourth clock pulse, this Q1 became 0 and Q2 became 1. And this Q3 continuing as 0. Okay. At last clock pulse, at 5, see the status Q1, Q2 0, but Q3 is 1. So this Q1 continuing as 0 and Q2 became from 1 to 0 and this Q3 became from 0 to 1. Okay, that values we wrote here. Okay, so finally when we observe this timing diagram, who will give the output? Q3 will give the output. Okay, first we are getting this bit. At third clock pulse only we are getting this bit now. See where we getting LSB? At third clock pulse, straight to this third clock pulse, we are getting LSB. Okay, so straight to this third clock pulse, we are getting this LSB 0. Then MSB here we are getting. Okay, we applied whatever the data we applied 100, same 100 came here. Here also we can see here 100 we have to see like this 100 and here 100 we have to see like this. Okay, and here 100 we have to see like this Okay, so we given input serially bit by bit and we got output bit by bit serial out. So serial in, serial out.